In 1974, Stephen Hawking proposed that black holes slowly evaporate. They emit radiation, a faint thermal glow at the event horizon, and over unimaginably long timescales, they shrink and eventually disappear. His colleagues were delighted. It was a beautiful result, connecting gravity, quantum mechanics, and thermodynamics in a single equation. Then they realized what it implied. If a black hole can disappear completely, taking everything that ever fell into it, every star, every planet, every atom, then all the information about those things disappears too. Permanently. Irrecoverably. And if information can be permanently destroyed, then everything you have ever known, every memory you carry, every pattern of synaptic connections that makes you who you are, could be erased as completely as if it never existed. Hawking spent the next 30 years trying to prove himself wrong. What he found changes what we can say about what survives. To understand what Hawking was wrestling with, you need to understand what a memory physically is, not what it feels like, what it is made of. A memory is not stored in a single location in your brain. It is not a file in a folder. It is a pattern, a specific configuration of synaptic connections between neurons, strengthened through a process called long-term potentiation. When you experience something, a face, a sound, a summer afternoon, neurons fire together. At each synapse where the firing is strong enough, a molecular cascade begins. Calcium ions flood the postsynaptic neuron, activating enzymes called kinases, which activate a transcription factor called Keb, which enters the cell nucleus and triggers the synthesis of new proteins. These proteins physically restructure the synapse, thickening the dendritic spine, inserting more receptors into the membrane, strengthening the connection. The synapse that fired together becomes easier to fire again. The pattern is physically inscribed into the architecture of your neural network, one protein at a time. When you remember something, your brain does not retrieve a stored copy. It reconstructs the pattern. The same network of neurons fires in approximately the same configuration it fired during the original experience. The reconstruction is imperfect. Memories drift, blur, merge. But the physical substrate is real. Proteins at synapses, ion channel configurations, electrochemical states distributed across networks of billions of neurons connected by trillions of synapses. Paul Reber, a neuroscientist at Northwestern University, estimated in 2010 that the total information storage capacity of the human brain is roughly 2.5 petabytes, 2.5 million gigabytes, enough to store 3 million hours of continuous video. The actual information content depends on how you count synaptic states, dendritic branching patterns, glial cell contributions, neuromodulatory tone, and other factors. Neuroscience has not fully quantified, but the order of magnitude is established. Your brain, right now, contains a specific quantity of information that is physical, measurable in principle, and subject to the laws of thermodynamics. It is not metaphorical. It is information in the same rigorous sense that the sequence of bases in your DNA is information, or the arrangement of atoms in a crystal is information. A pattern encoded in matter. And matter obeys conservation laws. There is a number, a specific calculable number, for how much information can exist in a given region of space. And the man who calculated it did so before anyone was thinking about brains or memories. He was thinking about black holes. In 1972, 2 years before Hawking's radiation paper, a physicist named Jacob Bekenstein at the Hebrew University of Jerusalem asked a question that sounded absurd. Does a black hole have entropy? Entropy, in thermodynamics, measures the number of possible microscopic configurations a system can have while appearing identical from the outside. A glass of water looks like a glass of water, but the precise position and momentum of every molecule in it is a specific arrangement, one out of an astronomically large number of possible arrangements. The number of those possible arrangements is the entropy. And Bekenstein realized that entropy is the same thing as information. The entropy of a system equals the amount of information you would need to fully specify its internal state. You see, this changes everything that follows. Because if entropy equals information, then information is not an abstraction living outside the physical world. It is a thermodynamic quantity, subject to the same laws as heat and energy and work. The information stored in your brain generates entropy when it is created, maintained, and eventually dispersed. It has a thermodynamic cost. Your neurons spend roughly 20 watts of power just maintaining the synaptic configurations that store your memories. 20 watts of metabolic energy converted to heat, 20 watts of entropy generated continuously to keep the pattern intact. When that energy supply stops, the pattern degrades. But the information itself, the entropy it represents, is conserved. It does not vanish. It redistributes. Bekenstein calculated the maximum amount of information any region of space can contain. The answer, now called the Bekenstein Bound, is proportional to the surface area of the region divided by 4 times the Planck area. The Planck area is roughly 10 to the minus 70 square meters. A square so small that if an atom were scaled up to the size of the observable universe, the Planck area would still be smaller than the original atom. It is the smallest meaningful unit of area in physics, the point where the fabric of space-time itself becomes granular. What emerges from the bound is staggering. A sphere the size of a human brain at the Bekenstein limit could theoretically contain roughly 10 to the 69th bits of information, a number so large it dwarfs anything in ordinary experience. Your brain operates at perhaps 10 to the 15th bits, billions of times below the theoretical maximum. But the principle is what matters. Information is not abstract. It is physical. It has calculable limits tied to the geometry of space-time, and it is subject to the same conservation laws as energy and matter. Here is the foundation Hawking's paradox crashes into. Hawking's radiation, the thermal glow a black hole emits as it evaporates, is featureless. It carries no detailed information about what fell in. It is thermal noise, random, structureless, identical, regardless of whether the black hole swallowed a library or a rock or a human brain. The radiation has a temperature, and that temperature depends only on the black hole's mass, not on the complexity or history of anything it absorbed. A black hole that swallowed Shakespeare and a black hole that swallowed an equal mass of hydrogen gas would emit exactly the same radiation. The information about the difference between Shakespeare and hydrogen, the information that I as Shakespeare, would be gone, not scrambled, not encoded, destroyed. This violates a principle that sits at the foundation of quantum mechanics, unitarity. Unitarity means that quantum evolution is reversible, that the laws of physics, run backward, can always reconstruct the past from the present. If you know the complete quantum state of a system now, you can in principle calculate what it was at any previous time. Information is never lost. It is the quantum version of the conservation of energy, except what is conserved is not energy, but information. If Hawking was right, and black holes destroy information, then unitarity is wrong. And if unitarity is wrong, quantum mechanics itself has a crack in its foundation. For 30 years, this was the black hole information paradox, arguably the most important unresolved question in theoretical physics. Hawking stood on one side, information can be destroyed, and quantum mechanics needs modification at the deepest level. Leonard Susskind, a theoretical physicist at Stanford, stood on the other. Information is always conserved, and Hawking's calculation must be incomplete. The radiation must carry the information out in some form too subtle to see in the original calculation. Susskind did not treat this as a polite academic disagreement. He later described it as a war. He titled his book, The Black Hole War. For 3 decades, conferences were organized around the single question of whether information survives a black hole. New theoretical tools were developed, the holographic principle, black hole complementarity. Each one an attempt to show how information could escape without violating general relativity. The most powerful argument came from Juan Maldacena, an Argentine-American physicist who in 1997 proposed the Adzak-CFT correspondence, a mathematical duality proving that a gravitational theory inside a volume of space is exactly equivalent to a quantum theory on the boundary of that volume. The boundary theory conserves information. Unitarity holds there without question. If the boundary and the interior are mathematically the same theory, then the interior must conserve information too. Maldacena did not show the mechanism by which information escapes a black hole. He showed that it must, that any consistent theory of gravity conserves information because the equivalent boundary theory does. The argument was mathematical, not physical, and it was devastating to Hawking's position. Hawking and Susskind made a public bet. The stakes were the consistency of quantum mechanics itself. In 2004, at a conference in Dublin, Hawking stood up and conceded. He had been wrong, or at least almost certainly wrong. New calculations, particularly from Juan Maldacena's work on the Adzak-CFT correspondence, strongly suggested that information is not destroyed by black holes. It escapes, encoded in correlations within the Hawking radiation, patterns so deeply scrambled that they are indistinguishable from thermal noise by any measurement, but theoretically present. The black hole does not erase, it encrypts. The information survives, smeared across the radiation in a form that is in principle recoverable and in practice permanently unreadable. Susskind had won. Unitarity held. The physics community reached a consensus that has only strengthened since. Information is conserved, always, in every physical process, without exception, now. What does this mean for the information in your brain? You are sitting somewhere right now. There is a specific memory, one that matters to you more than most, encoded in the physical structure of your neural tissue at this moment. A face, a voice, a day that changed something. That memory exists as a particular configuration of synaptic proteins, maintained by Krebs-mediated gene expression, stabilized by dendritic spine architecture, reactivated every time you recall it. The memory is as physical as the chair you are sitting in. It is made of matter arranged in a pattern, and that pattern is information, and information obeys conservation laws. Every person over 60 has asked in some form, will this be lost? The answer from physics is precise and strange and not entirely satisfying. The pattern that constitutes your memories, that specific configuration of synaptic weights, protein structures, dendritic branches, and electrochemical states, is physical information. It is subject to the same conservation principles that Hawking, Bekenstein, and Susskind spent 30 years establishing for black holes. When your brain ceases to function, when the electrochemical activity stops, when the sodium-potassium pumps that maintain the ion gradients across every neural membrane run out of ATP and shut down, when the proteins at each synapse begin to denature in the absence of metabolic maintenance, the pattern degrades, not all at once. The ion gradients collapse within minutes. The carefully maintained voltage difference of -70 millivolts across each neural membrane equalizes as ions flow freely through channels that are no longer being pumped. The synaptic proteins, the physical substrate of your memories, denature over hours as temperature drops and pH changes. The lipid membranes of your neurons lose their integrity. The information that was your memory of a face, a voice, a summer afternoon, scatters into the thermal and chemical environment. But scatter is not the same as destroy. And the difference between those two words is the entire content of the black hole information paradox. The atoms that held the pattern disperse into the environment. The thermal energy released by the dying cells, roughly 70 watts during life, dropping to 0 over hours, radiates outward as infrared photons. The chemical bonds that maintain synaptic configurations break, and the freed molecules enter new configurations. Glutamate is metabolized by soil bacteria. Lipids from myelin sheaths are oxidized. Calcium ions that were precisely positioned in presynaptic terminals diffuse into the surrounding fluid. The ion in your blood's hemoglobin oxidizes. Every atom that was part of a synapse that held part of a memory becomes part of something else. But, And this is where unitarity speaks. The information about where each atom was, what bond it held, what configuration it maintained, is not erased. It is encoded in the positions, momenta, and quantum states of every particle involved in the dispersal. Physics draws a careful distinction, destroyed versus unrecoverable. A burned book's information is not gone. It is in the ash, in the precise pattern of carbon deposits on each fragment, in the specific wavelengths and directions of every infrared photon emitted during combustion, in the trajectories of every smoke particle. If you could measure the exact quantum state of every particle involved, every ash flake, every photon, every air molecule that absorbed heat, you could, in principle, reconstruct the original text. Laplace's demon, the hypothetical observer with perfect knowledge of every particle's position and momentum, could run the physics backward and read the book from its ashes. Your memories after death are in the same category. 2.5 petabytes of synaptic information, the Krebs-mediated protein structures, the dendritic architectures, the receptor densities at each of your 100 trillion synapses, become encoded in the thermal radiation of cooling tissue, in the chemical products of decomposition, in the quantum states of atoms dispersing into soil and air and water. The pattern is not erased from the universe. It is diluted into the universe, spread across so many particles that extracting the original pattern would require simultaneously measuring more quantum states than there are atoms in the galaxy. Imagine it at scale. The information content of a single memory, the face of someone you love, encoded across the synaptic weights of perhaps 1 million neurons. After dispersal becomes spread across roughly 10 to the 30th particles in the surrounding environment. To reconstruct that one memory from its scattered state, you would need to measure and reverse the trajectory of every one of those particles, with precision exceeding anything that could exist in the observable universe. The information is not behind a locked door. It is dissolved into the ocean, gone in any humanly meaningful sense, present in the physics. Your memories after death are in the same category, dispersed, scrambled, encoded in the world at a scale that no instrument could ever measure and no computation could ever untangle. Gone in any humanly meaningful sense, not gone in the physical sense. The physics does not say your memories survive in a way that matters to you. It says they survive in a way that matters to the equations. Think about what that means for you right now. The face you remember, a specific person, a specific expression, encoded in a specific configuration of synaptic proteins distributed across perhaps 1 million neurons in your temporal cortex. That pattern does not cease to exist when your brain stops functioning. It ceases to be readable. The information transitions from an organized, accessible living state to a dispersed, inaccessible thermodynamic state. The same transition a book makes when it burns. The same transition a black hole's contents make when it evaporates into Hawking radiation. The pattern is not erased. It is encrypted by the second law of thermodynamics into a form so thoroughly scrambled that extracting it would require reversing the entropy increase of every particle involved. And yet, the laws of physics do not forbid the reversal. The second law makes it overwhelmingly improbable. The computational resources required exceed anything that could exist. But the laws themselves, the equations that govern every particle interaction, are time reversible. They run forward and backward with equal validity. The information is there. The universe contains it. The scrambling is not a wall. It is a number, a probability so astronomically small that it is indistinguishable from zero for any practical purpose, but mathematically, physically, fundamentally not zero. Hawking spent 30 years on this question for black holes. The answer, information survives but becomes unreadable, applies with identical force to every physical system in the universe. Your memories included, your identity included, the specific configuration of matter that is you, right now, reading this, all of it subject to the same conservation law that Susskind fought for and Hawking eventually conceded. There is a way to make this concrete. Write a single word on a piece of paper. Someone's name, perhaps. Burn the paper. Watch the flame consume it. The name is gone in every practical sense. But the laws of thermodynamics say this: Every carbon atom in the ink is now in a molecule of CO2 in the air above the flame. Every cellulose molecule in the paper has been oxidized, its atoms redistributed among combustion products. The thermal energy released, the heat and light of the flame, radiated outward as photons, each one carrying a specific wavelength and traveling in a specific direction, determined by the exact molecular configuration at the instant of combustion. If you could track every molecule of gas, every particle of ash, every photon, and measure their positions and momenta at any moment after the burning, you could reconstruct the name, not because of magic or mysticism, because the laws that govern the burning are time, reversible, and time-reversible laws conserve information. Now apply the same physics to your brain. 2.5 petabytes of information. Every face you have loved, every conversation you remember, every morning you woke up and knew where you were and who you were, encoded in the synaptic architecture of roughly 86 billion neurons connected by roughly 100 trillion synapses. When the system stops, that information undergoes the same dispersal the burned word underwent, at a scale roughly 10 to the 15th times more complex. The glutamate that held the signal at a synapse that held the memory of your mother's voice is metabolized by soil bacteria within weeks. The calcium that triggered neurotransmitter release at a synapse you used every time you recalled a summer afternoon diffuses into groundwater. The thermal energy of your last neural firing radiates as infrared photons traveling outward at the speed of light. Every one of those particles carries, in its quantum state, a trace of the configuration it came from. The physics is unambiguous. The information does not disappear. It disperses into the environment, encoded in the states of particles now scattered beyond any measurement, not gone. Unreadable. Every physicist working on the information paradox would agree with both of those statements. The disagreement, if there is one, is only about what the word unreadable means in a universe where the laws of physics are, at the deepest level, reversible. This is not comfort, exactly. It does not mean your memories survive in any way you would recognize, or any way that would matter to you, or any way that would matter to you, or anyone who knew you. The pattern is dispersed beyond any conceivable recovery. The face is gone from the world in every way that faces exist, as images, as recognition, as the warmth that arrives when someone you love walks into a room. In every human sense, the memories are gone. But physics does not speak in human senses. It speaks in conservation laws. And the conservation law that Hawking, Bekenstein, Susskind, and Maldacena spent 30 years establishing says this: the information content of the universe is constant. Nothing is added. Nothing is subtracted. Everything that has ever existed, every pattern, every configuration, every memory held in every brain that has ever lived is still encoded somewhere in the current state of the universe, not readable, not accessible, not meaningful in any way that would comfort a grieving person, but present. Physically, mathematically, irreducibly present. The universe does not forget. It encrypts. It encrypts. It encrypts. And the key, if it exists at all, is scattered across more particles than there are stars, not gone, unreadable. That is the physics.